think that things that feel visual. I like things move slowly. You know, such as brought like communities and everything and is. I know what you're looking to share. And then I had and then I had like on alcohol removal, so.
Yeah, could we do like a group picnic day?
Well, you gotta do it fresh, there's good songs. And when they probably the flavor's really good, just saying. Yeah, I know. Please look at it, so that's. Yeah. You know, I.
Yeah. Oh, man, oh, yeah.
I have also.
Okay. I know that. And I like, oh, please do.
I'm saying. I did like 3.5 years of journalism degree. Rob done it with 4 years. I understand. And you guys like more? Yeah.
Let's do it. All right, let me know. On this.
Which ones?
I got the beat one. Oh, actually, see, no, I didn't, I got the.
Oh my god, you got a whole good so worth
I asked how it's gonna be.
This is not getting the best.
Yeah.
Yeah, see, this man over here actually brought up the whole lot of change. Well, that so,
Or except.
I couldn't think of me about 6 licenses. You're saying that Alex gave it to you, but.
I was like, how
actually
he, I
don't.
was like, well, I think it's like, sure, it's so much. Wow. Big job. Can't believe we got one piece.
Don't know, it'd be like that.
All right, we are having some technical difficulties. So I am connected directly to the tablet. All right, does anybody have dry erase markers?
I do.
You do.
I have one.
You have one? Does anyone have another? No, nice. Yeah,
Okay.
who else? Who else had dry erase markers?
Just won't connect.
This is, I think this is the connection, like they call it like air media. But whenever I switch to some other method of connecting US or HDMI or USB C, it doesn't change anything. It just shows the kind of wireless connection, which I can't do. I mean, okay, I can try, I suppose. I really don't want to, but I can try. No, I could try seeing if we can connect to the air media thing. Oh god, I don't want to watch a damn video.
Can't you connect the HTTPS?
What's that?
Can't you connect the HTTPS?
Okay, let's try. We'll give it a shot. HTTPS. So what is it? 1081.131. Not private. Oh, I need a code 4506. Oh, look at that. Cool. Thank you for that suggestion. Okay, so let's get rid of this. And let's get rid of this. Zoom. Oh, hold on. Okay, well, we'll see how this goes. Right, so I'm going to keep these dry erase markers until we get through this. Thank you very much for those of you that offered them to me. Remind me to return them at the end of the class. Okay, so what we're doing today is we're doing our transition from analog electronics, where voltages and currents can take on any values, to digital electronics, where we are going to deal with voltages that are either a low or a high, a 0 or a 1. And we kind of began this a little bit last week, where we talked about diodes, where the current is either off or on, depending on the direction that you try to send the current through the diode. The diode is a semiconductor device. We haven't talked about how you make semiconductor materials or what's special about them. We will begin that probably Wednesday or after the reading break. The devices that we're going to use in digital electronics are also constructed from semiconductors. In particular, they're not going to be diodes, but they're going to be transistors. And what we'll do is, when we talk about semiconductors, we will see pretty explicitly how we can form, how do we create a diode, and then how do we create the transistor. The diode is used for the rectifier circuits that we worked on in the lab last week. The transistors, the way that we're going to use them is we're going to build these so-called logic gates, which we'll describe today, that will process our digital signals. So let's see if we can get this started. Okay, so in digital electronics, we will work with voltages that are in only one of two states, one of two possible states. Okay, so we're going to have a low, which will denote as a 0, and a high, which will denote as 1. So originally, the low and high voltage levels used to correspond to 0 volts and 5 volts. And that standard still exists today. However, as you shrink your devices and components down to smaller and smaller voltages, smaller components can't dissipate as much power. And so what you try to do is you try to make your devices so that they have to handle as low a power as possible. And so a common high level voltage these days, I think, is like 3.3 volts. And that's just to get the power dissipation down in these small handheld devices that pack thousands of components into a small space. Okay, for us, what we will typically work with, typically 0 volts will correspond to a low, or which we'll call a 0, and 5 volts will correspond to a high, which we'll denote by a 1. All right, and so what we're going to have to do is we're going to have to process these digital signals, and we're going to use logic gates to do that. Digital signals are processed using logic gates. And you may have, depending on what kind of courses you've taken in the past, you may have encountered these logical operations in the past. So let's see what happens. Can I get rid of this? Yeah. Let's get rid of that. All right. Okay, so types of logic gates. So 1. The simplest one is the NOT gate or the inverter. What the inverter is going to do is if you input, say, a digital low, that will be inverted to a digital high at the output, and vice versa. If I input a high, I'll get a low at the output. So the NOT gate or the inverter has 1 input and 1 output. And it looks like this. It's this little triangle thing with a circle on the end. This is going to be our 1 input. And maybe I'll call that A. And then over here we have our output is the inverse of A. And so this little bar that I put over the A means not A, or the inverse of A. So this denotes not A. Maybe I should say, I'll put capital not. Okay. Now, one thing that we have to recognize is that we've kind of used this triangle symbol before. Where have we seen the triangle symbol if we didn't have the little bubble on the end? That's an op amp, okay? So we just have to know by context that this is not an op amp. A couple of ways to kind of remind ourselves, it does not have, this presence of the bubble means that it's not an op amp for sure. And it only has a single input. So this is a logic gate, not an op amp. Okay, for these logic gates, what we usually do is we construct a so-called truth table. One side of the truth table will list all of the possible input states, and on the other side, we'll write down the corresponding outputs. So here's the truth table for the inverter. So this will be the list of the possible inputs. What are the possible inputs for a device that has only 1 input? What could A be? Low or high, that's it. So in this case, we have only 2 possible inputs, and that exhausts all possibilities. And then at the output, we're going to have not A. So if the input is a low, then our output is going to be a high. And if the input is a high, it gets inverted to a low. Okay, so all possible input are listed on the right, sorry, the left of our table, and the corresponding outputs are listed on the right. Listed on the right. Okay, so all the inverter does is it changes the state of the input. Okay, so some of the more interesting ones are going to be devices that have multiple inputs. And so we're going to have our second logic gate is the AND gate. And its symbol looks like this. So I'll draw two inputs, A and B. And then we'll have a single output. And this output is going to be denoted as A dot B. The way you read this is A and B. It looks like multiplication, but it's a logic operation. It's not a direct multiplication. But we'll see why they use this notation in just a second. So we read as A and B. So this is the logic operation of AND. So it's not multiplication. Okay, so if we were to construct the truth table, we would have on the left, we're going to list all of the possible outputs, and on the right, we will list the corresponding outputs. So what are the possible combinations of inputs for our AND gate? Which one possible combination of A and B?
0, 0.
0, 0. What's another one? Yeah, we'll put 1, 1 down here. What else?
1, 0, and 0, 1.
Yeah, so I'm going to put them in this order. And so when you hear AND, when would you expect the output to be a high if you have an AND operation?
Both must be true.
Both must be high in order to have a high output. And so if A and B are both high, then the output is high. Otherwise, the output is low. So the output is low unless both A and B are high. We can also get a sense of why they've used the multiplication type notation. Let's think of if I took A multiplied by B, 0 times 0 is 0. Oh, that works. 0 times 1 is 0. That works. 1 times 0 is 0. That also works. And here 1 times 1 is 1. So in this case, this works all of the time. So we could, if we wanted to, think of this as like a multiplication type operation. We'll see why I'm going to distinguish the AND logical operation from multiplication in just a second, because it doesn't work in all cases for all possible operations. All right. So if we have an AND type operation, what other types of operations could you imagine? Instead of A and B, what could we do? Yeah, we could do OR. And so that's another one of our logic gates. So we have the OR gate. The OR gate looks a bit like this. So it's got these kind of curved sides instead of these straight triangular sides. It's another 2-input device and a single output. And it's going to be A or B, where we're going to use the plus sign to denote the or the logical or operation. So this is read as a or B. And so this is the logical or operation. It's not addition. But again, there is a bit of a reason for using that kind of notation, and we'll see it when we write down this truth table. We'll also see the limitation of having a literal interpretation of addition here. All right, so for a 2-input logic gate, the possible combinations of inputs that we listed for the AND gate are the same here. So for any 2-input logic gate, the possible combinations of inputs are always the same. So if the output is equal to A or B, when would you think that the outputs are going to be high? Which ones of these are going to be high? Is this one going to be high? This one? Yep. 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 Okay, so we're going to get 0, 1, 1, 1. Let's check this addition property. 0 plus 0 is 0, that's good. 0 plus 1 is 1, 1 plus 0 is 1, those two are good. But 1 plus 1 is 1, so that's where kind of the literal interpretation of addition breaks down. So we have to know that this is an or logical operation, not strict addition. All right, good. So what we're going to do next is we're going to write down a few more of these logic gates that we can encounter. And the next one is going to be called the NOR gate. And what NOR means is not and. Okay, the way we're going to draw it is it's going to look just like the OR gate. So there's the two inputs, A, B. The OR gate looked like this kind of D type symbol. To the way we indicate that it's a not. Sorry, what am I doing? Sorry, I'm so confused. I'm being dumb. We did the AND gate first, right?
Is that a NAND gate?
Yeah, we're going to do NAND gate. So let me fix this. That's confusing. We're going to do a NAND gate, which is a not AND. Okay, so I'm going to start by drawing the AND gate that looked like this D symbol. And then to indicate that it's a not AND, we put a little bubble on the end. And that's kind of a nice notation because it comes back to our original inverter or NOT gate. And really what this circle means is invert. So the way we interpret the NAND gate is we do the AND operation and then we invert all of the outputs. So this is going to be the output. It's going to be A and B. And then the line over top means do the inverse of that. So first evaluate A and B, and then take the inverse. So if we did the truth table, what we could do is we could first copy down the truth table for the AND gate, which you already told me looks like the following. So the AND is only high when both inputs are high. And then what we have to do is we have to take that AND operation and invert it. So all we're going to do is take all these outputs and switch their state. So this AND gate is really equivalent to taking, so the NAND gate is equivalent to taking the AND and then putting an inverter on the end. So this would be A, B. Over here, we would have A and B. And then over here at the output, we would have A and B. Not. Okay. Good. So I mean, you could probably guess if I could do a NAND gate, I could also do a NOR gate. But before we do that, I want to tell you that this NAND gate is a special one. The reason it's special is because it's possible to use a NAND gate to construct all other possible logic operations. So we've seen the NOT and the OR, and so it should be possible to use only a NAND gate to make those operations, and not only those two, but all of the other ones that we're going to write down. So what I'm going to show you is I'm going to show you that we can make a NOT gate using a NAND gate. And then in lab 7, which we're going to do on Thursday, you're going to use only NAND gates to make an OR gate. And so I'm not going to show you that one. I'm going to see if you can figure that one out on your own. So note. All of the other logic gates can be constructed using only NAND gates. So therefore, the NAND has become the industry standard. In fact, if anybody, yeah, go ahead.
Wouldn't using only NAND gate increase the complexity of the circuit?
Does it increase the complexity of the circuit? Not really. And the reason is that we will see once we've talked about transistors, the way that we're going to make the NAND gate is by using 2 transistors. And so what we can do is we can use those 2 transistors and combine them in a way that performs all those other operations. Maybe if we use a NAND gate to make, say, an OR gate, there's extra transistors, but it turns out to be convenient. Has anyone ever heard of these FPGAs, these field programmable gate arrays? So I've never used them, but they're quite popular in that what I believe it is just a board that has like literally thousands of NAND gates on them. And then in software, you program how they get hooked up and you can make whatever complicated logic operation you want using only the NAND gates. And so you have this one device that can basically do any kind of logic operation you want. Okay. All right, so let's see how this works. Let's see in a simple example. We're going to try connecting the A and B inputs of a NAND gate together. Okay, so what do I mean by that? Let's just take our NAND gate. Here's input A. Here's input B. But what I'm going to do is I'm going to take B and I'm going to force it to be equal to A. All right. And then we're going to have our output, which is A and A this time, and then not. Okay. So let's try the truth table. A and B. Okay, so what are the possible inputs going to be this time? Let me just write down all the ones we've been using, and then we'll have to exclude some of them. So which one of these are not allowed? There's a couple that aren't allowed. Which ones?
The middle one?
The middle ones, yeah. So we need A and B to be equal. And so these 2 middle ones have A not equal to B, and so they're excluded. All right. And so if we were to write down the possible outputs, if we just list them all, this was the NAND gate truth table. And so we're gonna get rid of those two. All right, so out is A and B not. So we can condense this into a smaller truth table where there's only one input and it's A, and it can be 0 or 1. And this is our output is A and A not. Well, if A is 0, the output's 1. If A is 1, the output is 0. So what have we made? What is this the truth table of? It's an inverter. Yeah, it's the NOT gate, right? And so therefore, this is the truth table of a NOT gate. And so therefore, what we can say is if we take a NOT gate and force its two inputs to be the same, it outputs not A, and that's exactly equivalent to our inverter, which was our first logic gate. Okay, good. So what we'll do is, well, okay, we'll say exercise for the student. And you should try this one because you're going to need to do this for lab number 7. So the task is to design an OR gate using only NANDs. So I can give you some hints. You're going to need 3 NAND gates to do it. Another hint is we'll make use of the NOT gate above, right? So you can construct NOT gates from NAND gates. We know how to do that now. That is going to be useful for this little exercise. And so this is not a hint, but experiment number 7 on Thursday. You'll have to actually build this OR gate using only NAND gates. And let me encourage you to actually just sit down and try it. Like, of course, you can go online or you can go to ChatGPT and say, build me an OR gate from NANDs, and it'll tell you how to do it. But if you take those shortcuts, all you're doing is you're training yourself to always take shortcuts, and that's not what you want to be doing. So take some time, see if you can solve this little puzzle. It's not too difficult. Okay, so let's just finish up. There's 3 more sort of common logic gates, and so let's just write them all down so that we have them in one place. So other logic gates. So we've done NOT, AND, OR, NAND, and so NOR is the next one. And I'm sure you could tell me everything about this NOR gate already. So I'm going to draw an OR gate. How would I indicate that it's a NOR gate? What do I have to add? A little bubble, right? So here's our output, and this is going to be A or B not. All right, and so here the bubble is a not. All right, truth table. So we'll do A, B, and then we'll do A or B, and then we'll do the output is equal to A or B not. So the possible inputs for a 2-input device are always the same. The OR required one or both of the inputs to be high. And so that's what it looks like. And so the not or is just the exact inverse of that. And so it's 1, 0, 0, 0. All right. So there's only a couple more, and the next one is called the XOR. It is the exclusive OR gate. Exclusive OR. The symbol is we start with an OR gate that looked like this thing. And then this one's a bit weird. There's this little extra curve bar on the left-hand side. And then your two inputs come off with that. And so this is AB. And this is our output. The way they write it is A or B. And to indicate that it's an exclusive OR, put a little circle around the plus sign. So this is the exclusive OR operation. All right. So let's write down the truth table. So this is going to be A, B, and this is our output is A exclusive or B. So inputs are always the same possibilities. Now, when you hear exclusive OR, what would you guess is going to be the difference between the OR gate? Let me write down here. This is not the right set of outputs, but let me write this down. This is the OR gate outputs. Which one of these is going to be modified, do you think? The 1, 1 is going to be not a 1, but it's going to be a 0, and that's exactly right. So the exclusive OR is the same as the OR outputs, but it excludes the 1, 1 case from being high. And we'll actually see that we'll come up with an application where this is a useful operation. So some of the things that we'll try to do is, for example, if we had two sets of digital numbers, which we represent in binary, we'll talk about the binary system shortly. How could we add those? And so we'll come up with these summing circuits that are going to add these logic signals for us, and gates like this will be useful. Okay, so this is like the OR gate output, except the last line is excluded from being a high. All right. So if we have an OR and a NOR, an AND and an AND, and XOR, what's the last one we're going to write down? What do you think it's going to be? Yeah, it's a not XOR. They call that one an XNOR. I guess because it's hard to pronounce. NOR. I don't know how would you read it? XNOR is the way we're going to call it. So this is not an exclusive OR. All right. So it's going to look just like the XOR, but it's going to have the bubble to represent the not. This will be AB, and this will be the output is going to be A XOR B not. Okay, and then the truth table is exactly what you think it'll be. AB. I guess we could do A XOR B, and then we could do the output is going to be the inverse of that. So out will be equal A XOR B not. 0 0 0 1 1 0 1 1. So exclusive OR. is 0, 1, 1, 0. And so if we invert that, we get 1, 0, 0, 1. All right, so let's see. Let's see if we can get ready for the lab on Thursday. And so we'll start the following way. So let's talk about experiment number 7 on Thursday. And this is digital basics. Do you have a question? Yeah. Okay. All right. So, so part 1 of the lab will be to test one of the available logic gates. What we have in the lab are only NOT gates and NAND gates. So you're gonna have to test one of those. So it's either the NOT or the NAND. So one of the things that I wanted to point out, the reason that I'm writing this down is that there's kind of a nice way to monitor the outputs of logic gates. You know they're either going to be a 0 or a 1, say 0 volts or 5 volts. And we want a quick way where we could just look at it and know instantly whether the output is high or low. Okay, so I'll make some general comments about these logic gates, and then we'll talk about how we can monitor the output in a convenient way. So logic gates require plus 5 volts and ground to operate. So just like when we were using the op-amp, we had to power the op-amp. In that case, it was plus minus 15 volts in order for it to operate properly. For the logic gates, they need 5 volts and ground to function the way they're intended to function. So what we have to do is we have to check the data sheets to identify where the plus 5 and ground go. All right. So let me just show you. Let's see if I can. I want to share this screen. And let's go to the course website here. Will it let me do a new tab? Yes. And we'll go to 231 here. All right. So datasheet archive. So you can go here and you can find data sheets for the various components that we're going to use. We've already used the op-amp, so that's its data sheet. Let's say you were going to build and test the NAND gate. I guess not build it, but just test that it works. So this is what the data sheet looks like. You're going to get a little chip, and each chip is going to have 1, 2, 3, 4, 5, 6, 7, 14 different pins on it. And so they're going to look like this. They look exactly like what you use for the op-amps. Just those op-amps had only 8 pins. These ones have 14. And if we look at this, this is telling us that we have 4 different NAND gates on a single chip. So if you're building something that required, say, 3 NAND gates for some reason, like the OR gate you're going to build, it needs 3 NAND gates. So you can get them all from a single chip. You don't need 3 separate chips. And this is telling you where the inputs and output of the first NAND gate are. So pins 1 and 2 are the inputs of the first NAND gate, and pin 3 is the output. For the second NAND gate, 4 and 5 are the inputs, 6 is the output, and so on. That takes up 12 of the 14 available pins. There's 2 left over. Pin 14 is VCC, that's your +5 volts, and pin 7 is the ground. They probably have here, yep, here's a picture. So 14 is +5, 7 is ground. This is input, input, output of your first NAND gate. Input, input, output of the second. Input, input, output of the third. Input, input, sorry, I got that wrong. Input, input, output of the third. Input, input, output of the fourth. Okay. So those data sheets are always available for you to figure out those connections that you need to make. All right, so here we go. Now we're back here. So the other thing I wanted to say is that we can use a light emitting diode or an LED to monitor the output of a logic gate. We used regular diodes last week, and we know that what diodes do is they pass current in one direction and not in the other. What's special about an LED is that when they are passing current, they emit light. And when they're not passing current, they do not emit light. And so we can look at whether or not we have light on or off to tell whether the output is high enough to drive current through your LED, or if the voltage at the output is 0, then your LED has no current and no light. So let me draw for you what the LEDs in the lab look like. So it's going to be like this little red plastic case, and it's translucent, so you can see through that plastic case. And if you look through it, what you'll find is that there's kind of a set of 2 electrodes. There's a fat electrode and a skinny electrode. So there's the skinny one. And then the fat one looks something, I can't draw it perfectly, but it looks something like this. Okay. The other thing they do is they intentionally make the leads coming off of the LED different lengths. So this is the long lead. That's the positive terminal of your diode. This is like the p-dope side or the p side. If we make the p side positive with respect to the other side, then current flows. And then this short lead is the negative one, and that's the N side. Okay, the circuit symbol for an LED, like that's what it actually looks like when you go grab it out of the box. And this is what we are familiar with for the circuit symbol of a diode. To indicate that it's an LED, they have little arrows coming off the side that are supposed to represent, say, the light or the photons that are being emitted when the current is conducting. So when the positive terminal of an LED is higher in voltage than the negative terminal by an amount, we called it V threshold for a regular diode, so let's stick with that notation. Then the LED lights up. For the diodes that we used last week, the threshold voltage was somewhere around 0.7 volts. I think some people found that it was a little bit higher. maybe closer to a volt or something like that. For LEDs, it's even a little more. So for the red LEDs, I forget the exact number, but it's around 2 volts to turn it on. But that's okay because we're expecting our logic gates to output 5 volts when they're in the high state. So with all that, what we can do is the following. So to test a logic gate, we could say we're going to test the NAND gate. So the NAND, for example. A convenient way to do that is to take the output and connect it to an LED, and then take that LED to ground. So I'm going to draw it to ground, but I'm going to change this picture so you can wait a second before drawing this. This would in principle work, but if we had 5 volts here, the LED would turn on. And so we drop, say, 2 volts across there. So at the output, we'd have something like 3 volts sitting here. And that 3 volts is going to go directly to ground. If there's no resistance here, then the current would be very high. And that's not good for our logic gates. And so what we're going to do is we're going to put in here a little resistor. And so this resistor is something like 200 to 220 ohms. Its exact value doesn't really matter. All that matters is that it's there to limit how much current you get. And it's literally called a current limiting resistor. So we could actually figure out how much current we're going to get, because we could say if the output, so this is output, if the output is equal to 5 volts, then, well, let's see, we would have 5 volts minus whatever we drop across the diode, so minus V threshold, minus I times R, whatever voltage we drop across our resistor. And then that takes us to ground. So that has to be equal to 0. And if we solve for the current, that would be 5 volts minus V threshold divided by R. And so you can see here, if we make R equal to 0, that would in principle mean an infinite current. Of course, that's not going to happen. There's going to be a limit to how much current your logic gate can output, but we don't want to push that limit. And so this is us setting the value of the current that we're going to get. And 200 ohms-ish is about the right value for stable operation. Yeah.
What would happen if when you actually fry your?
Yeah, you could potentially damage some components. This thing, your little chip with all the gates on it might warm up, because as you increase the current, you know, inside these devices are going to be some resistors and so on. So if you have a high current, then you dissipate a lot of power. They start to heat up, and if they heat up too much, there could be some damage. So, yeah. All right, good. So what we'll do is we'll finish off our preparation for lab number 7 on Wednesday, and then we'll start talking about the actual construction of these logic gates and diodes and transistors and things like that. All right, thanks very much. Yes.